It's a great pleasure to have today's speaker in our Rutgers Experimental Math Seminar, the distinguished historian of mathematics from UCLA, Amir Alexander, who will talk about the experimental geometer, how John Wallis saved mathematics for the Royal Society. As usual, please unmute yourself, but if you have anything to add or comment or question, please unmute yourself and say it. Thank you.
All right. Well, thank you, Doron. Thank you so much for inviting me. So thanks, everybody for coming. Yeah, this is, I'm sure, a little bit different from most of the talks in this seminar. It is about history. It is about an early example of experimental mathematics and the motivations behind it. That is John Wallis, who developed this experimental approach, and he had philosophical and even political reasons for doing so. And that's what I'll be talking about today. So in the year 1645, can everybody hear me? The career of the young Presbyterian clergyman.
We hear you very well.
Okay, great. In the year 1645, the career of the young Presbyterian clergyman John Wallis appeared to have stalled. Only a few years before, while yet in his mid-20s, he had been a rising star in the circles of Puritan divines, serving as Secretary of the Westminster Assembly, charged with reforming the Church of England. But as the years passed and the Presbyterians' power waned, the prospects for the young firebrand Wallis dimmed along with them. It was in this challenging time, when Wallis was seeking alternative venues for his energies, that he joined a group of scholars pursuing what have been called the new philosophy or experimental philosophy. The group met regularly in private homes in London and Oxford throughout the interregnum and was known by different names at different times. In 1662, the returning monarch, Charles II, finally gave it official recognition, charter, and a name: the Royal Society of London. 3.5 centuries after its founding, the Royal Society is the most august scientific institution. But in 1645, when Wallis began attending the group's informal meeting, all this lay far in the future. The purpose of the meetings of the society, as the society's first historian, Thomas Sprat, wrote some years later, was not to find a scientific academy, and advancing the frontiers of knowledge was a secondary concern. Their first purpose, Sprat reports, was no more than breathing freer air, and of conversing in quiet with one another without being engaged in passions and madness of that dismal age. At a time when royalists and parliamentarian, Presbyterians and independents, Puritan and enthusiast, property owners, tenants, and so on and so forth, were all at each other's throat, these men were seeking an escape. And they found it in the study of nature. Their meetings, Sprat reflected, were a place in which they could draw their minds off past and present misfortunes, converse quietly, voice opposing views without fear of violence, and find common ground despite disagreements. Amid the furor, fanaticism, and intolerance of revolutionary England, they had found a safe haven of tolerance. Meeting weekly at the home of one of their members or at Gresham College, Wallis and his friends discussed and experimented on the entire array of new ideas and discoveries that were shaking the foundations of the old medieval order of knowledge. There are only two fields, Wallis explained in his autobiography, that were intentionally left out: theology and state affairs. Under royal patronage, the Royal Society became a trend-setting scientific organization, and here we go. There's Wallis, there's Gresham College, and this is the Charles II. Under royal patronage, the Royal Society became a trend-setting scientific organization, and Wallis one of its founding members. Its regular meetings in these early years were often devoted to experiments executed by the Society's curator of experiments, Robert Hooke. Unlike modern scientific research, experiments in the early Royal Society were performed in public, that is, in front of an audience of Society fellows and sometimes notable guests as well. Those present would then discuss what they saw, examining its meaning, significance, and seeking common agreement. Now, to a modern experiment, this would seem more like a circus performance, but there was good reason for this peculiarity. For unlike its modern descendants, the Royal Society aimed not only at scientific research, but also at providing a model for the workings of the state. The mission has its roots in the meetings of the London group back in the 1640s. Outside their meeting hall, the group's members might be radicals or moderates, Presbyterians, independents, parliamentarians, royalists, all engaged in a life and death struggle for domination. But inside their meetings, none of that mattered. For nature alone, Spratt wrote, never separates us into mortal factions and gives us room to differ without animosity, without any danger of civil war. What started as a simple refuge ultimately developed into an ideal. If reasonable men of different backgrounds and conviction could meet together to discuss the workings of nature, why could they not do the same in matters of state without murdering each other on the battlefield? The founders of the Royal Society, the harmony that prevailed in the natural philosophers' meeting, even among men who disagreed sharply, seemed to hold an important lesson for the entire English body politics. The dogmatism of the preceding decades would be replaced by moderation, open-mindedness that characterized the meetings, their meetings and their science. The hubris of the fanatics would be replaced by the modesty of the experimenter, passions with rational debate, and intolerance of sects with tolerance of different but reasonable men. The public experiments of the early days played a crucial part in this political mission. They served as an example of how reasonable men could discuss difficult issues, debate them thoroughly, and ultimately come to a shared understanding. For such discussions to take place and for members to form their own opinions, it was therefore essential that the experiments be conducted before witnesses. Significantly, however...
Could I just make a comment here?
Sure,
yes. I think the role of Hooke here is absolutely fundamental, because he took great pains to find out what experiments were being done on the continent, to get details of them from the Low Countries in particular, and to set up them so they really would work. And he thought that this was, as a man essentially concerned with practical things, this was a way of increasing knowledge of science among his scientific contemporaries.
Yes, absolutely. He was the moving spirit behind that project. Yes. Significantly, however, not all forms of natural philosophy were equally suited for the society's goal of promoting peace and tolerance. Particularly suspect were grand philosophical systems that claimed to arrive at indisputable truths through the power of pure reason. One such system that was sweeping the continent at the time was Cartesian philosophy. An even more ominous system anchored in pure reasoning was the one advanced by Thomas Hobbes. Hobbes and Descartes differed radically on many critical issues, but this much they had in common: both believed that their system was structured like Euclidean geometry, founded on self-evident assumptions and proceeding through rigorous deduction to unchallengeable truths. Now, it was precisely this, here we go, there's Descartes and Hobbes. There's a Leviathan where through this totalitarian vision of the state that Hobbes deduced by what he considered strict geometrical reasoning. It was precisely this unquestioning confidence in the validity of their systematic reasoning and the absolute truth of their conclusion that the founder of the Royal Society found dangerous. It is, Spratt warned, a temper of mind of all others most pernicious. Such a confidence in one's reasoning leads to pride and dogmatism, which in turn leads to sedition and subversion of the state. It was not the kind of approach that would be practiced in the Royal Society. The alternative to the dogmatic rationalism of Descartes and Hobbes was experimental philosophy. Unlike the brilliance and dash of systematic philosophers, Spratt wrote, experimentalism is a laborious philosophy. that teaches men humility and acquaints them with their own errors. It teaches men to work hard, acknowledge their own failures, and recognize the contributions of others, precisely the attitudes that the founder of the Royal Society hoped to instill in the body politics as a whole. Unlike the rationalist philosopher, the experimentalist never claimed that his results are absolutely and irrefutably true, but humbly proceeds from experiment to experiment, trying to make sense of whatever they find. In place of the intolerant fanaticism of parties and sects which had thrown the Commonwealth into violence and chaos, experimentalism will breed moderation, cooperation, respect for differing opinions, and ultimately civic peace. Now, unfortunately, for the founders of the Royal Society, their preference for experimentation at the expense of rigorous reasoning created an unexpected problem. It left mathematics out in the cold. Mathematics, after all, was the ally and the tool of the dogmatic rationalist philosopher. It was the model of the elaborate systems of the rationalist, and the pride of the mathematicians was a foundation of the pride of Descartes and Hobbes. And just as the dogmatism of those rationalists would lead to intolerance, confrontation, and even civil war, so it was with mathematics. Mathematical results leave no room for competing opinions, discussions, or compromise of the kind so cherished by the Royal Society. Once introduced, they impose themselves with tyrannical power, demanding perfect assent and no opposition. This was precisely what Descartes and Hobbes had so admired about mathematics, but it was also what Boyle and his fellows feared. Mathematics, by its very nature, leads to claims of absolute truth, dogmatism, threats of tyranny, and, who knows, civil war. And yet, despite the ideological and political dangers, mathematics could not be dispensed with. Some of the greatest accomplishments of the new philosophy, after all, were heavily mathematical. Some advancement in medicine, such as Harvey's discovery of the circulation of the blood, were certainly experimental. So was William Gilbert in the investigation of magnetism. But the greatest scientific triumphs of the age, from Copernicus to Kepler's transformation of the cosmos to Galileo's law of falling bodies, were deeply indebted to mathematics. What then could the Royal Society leaders do? How could they embrace the important contributions of mathematical science and yet avoid its dangerous methodological, philosophical, and political implication? It was a conundrum that left the Royal Society with an ambivalence towards mathematics that characterized its science for many years. And no one felt this conflict more keenly than John Wallis. Wallis was the leading mathematician. I thank you for your giving credit to Brownker, but at least by reputation, he was a leading mathematician among the Society's founders, and it therefore fell to him to address the problematic status of mathematics. He fully shared his associates' abhorrence of dogmatism, and in his autobiography, he took pride in his moderation and openness to diverse opinions. And yet, as a mathematician, he was committed to a field that prides itself on its flexible methodology and the absolute and incontestable truth of its result. How is one to reconcile this with the moderation and flexibility he cherished as a member of the Royal Society? Wallis's solution was simple as well as radical. He created a new kind of mathematics. Unlike traditional mathematics, there's Wallis again. Unlike traditional mathematics, this new approach treated geometrical objects as physical objects in the world, not as ideal forms to be constructed. It proceeded not through rigorous deductive proof, but through trial and error. Its results would be extremely probable, but not irrefutably certain. They would be validated not through pure reason, but by consensus, and would be judged not by their logical perfection, but by their effectiveness at producing new results. It was a mathematics, in other words, designed to emulate the experimental approach practiced at the Royal Society. It would be a new experimental mathematics powerful and effective in the service of science, but also serving as a model for tolerance and moderation rather than dogmatic rigidity. So the singular nature of Wallis's approach is apparent from the very first theorem of the very first work he published as civilian professor of geometry at Oxford on conic sections in 1655. Do you see the whole slide here?
Yeah, it's clear.
Yeah. Okay. All right. Okay, so basically what Wallis is proving, of course, a result that he knows and everybody knows, that is the area of a triangle. But he decides to calculate it as the sum of an arithmetic series. That is, he wants to sum up of all the lines from B to V, this apex. And he says, as you do in arithmetic, the way you calculate an arithmetical triangle, you sum up an arithmetical series. You sum up the two ends, the smallest part and the larger part, and you multiply it by the number of terms, and divide by 2. Well, the apex V here, what is the magnitude? The magnitude is 0. The magnitude of the bottom is B. So together their sum is B. The number of lines, he wants to sum up the number of lines. How many lines are there? There are an infinite number of lines. So the sum of all the lines together is infinity divided by 2 times B. And by the way, Wallis is the person who introduced that sign for infinity. So that is the sum of the lines. And then the question is, well, what is the thickness of the lines? The thickness of the lines is if you take the whole height A and divide it by infinity again. Okay. And so you multiply the number of lines by the thickness of each line, and that's what you get. You get A over infinity, that's the thickness, times infinity times B divided by 2. Infinity cancels infinity, and what you get is A times B divided by 2. That's how he proved the area of a of a triangle.
Can I ask a question, please? Another question.
Sure.
You've written elsewhere about the very dangerous notion of the indivisibles of the continuum, and the problems that people have on the continent. Was there any echo of this, or was England immune from the problems of that Torricelli and Roberval and so on had on the continent?
Yeah. I mean, there was no effort, as I described, to suppress individuals, but it was certainly controversial, and there was certainly a lot of criticism of this. Much of it coming from the continent, because basically these are wild and woolly calculations, and I don't think modern mathematician would follow it, and certainly not many of his contemporary, including the Jesuits and Fermat. The Continentals, who are very critical of this. Apart from the problematic assumption of that a surface is made up of lines with a certain very small thickness, Wallis was also assuming that the rules of summing up a finite series apply to an infinite one, and then he was also, casually dividing infinity by infinity, which is to mathematicians now and then is undefined, but he had no problem doing it, and he was criticized for that, specifically by Fermat. But Wallis refused to concede any of those arguments, and pointing out that his results were, after all, correct. So, what has Wallis accomplished with his unconventional approach? For one, he posited that geometrical objects are objects out there in the world that can be investigated just like a natural object. Mathematical entities exist. not in the imagination, but in reality. They are like actual physical object, he wrote in the Mathesis Universalis. This is exactly the opposite of the traditional view that how the geometrical object should be constructed from first principles. For Wallis, a triangle already exists in the world, and the geometer's job is to decipher what it's made of. Look at it really closely and figure out what is it composed of. And you can think of it like like thinking of like strata, like geological strata. There is a rock, there is a cliff. What is it made of? It's made of these geological strata. Drawing on common sense and intuition about the physical world, he concluded that a triangle is composed of parallel lines, just one on top of the other, just as a rock formation is made of geological strata. Now, since geometrical objects for Wallis already exist in the world, it follows that mathematical rigor is quite unnecessary. I mean, in traditional geometry, Euclidean geometry, in which one constructs geometrical objects from first principles and proves theorems about the relationships, logical rigor is indispensable because otherwise you don't know if your results are correct or not. You just have to be very, very careful that every step is absolutely correct. The case, however, is very different when one is examining an object in the world, because it is external reality that decides whether the result is correct. Not your rigorous reasoning. You have this backstop of, is it true or not? An over-insistence on strict logical reasoning can be more of a hindrance than help. And since the triangle and its structure were, for Wallis, as real as a geological formation, rejecting it for transgressing on some minor point of rigor was as sensible as dismissing a geological theory for a typo in its printed abstract. Both were being overly pedantic, and it's ultimately silly. So Wallis's approach in the De Sectionibus Conicis, on conic sections, established geometrical objects as real bodies in the world, but it left open the question of how these investigations should be carried out. Now, in this particular case, he relied on sort of this kind of intuition of what a triangle is made of, this materialist intuition, and it proved to be effective, but it is not exactly a method. In the Arithmetica Infinitorum, published alongside the De Sectionibus Conicis in 1656, Wallis provided just such a method. Now, this is what he said about his methodology: the simplest method of investigation in this and various problems that follow is to exhibit the thing to a certain extent and to observe the ratios produced and compare them to each other, so that at length a general proposition may become known by induction. That's proposition 1 in the first page of the Arithmetica Infinitorum. Now, the critical word here is also the last, induction. And the approach became known to both Wallis and his critics as the method of induction. Now, he was not thinking about, modern mathematical induction, which is a perfectly rigorous method of truth. What in the 17th century, induction was associated specifically with the scientific approach advocated by Francis Bacon and his followers at the Royal Society. Now, just to a couple of slides here. Right. So deduction is, deducing necessary general principles and deducing necessary results from them about particular truth, as you do, for example, in Euclidean geometry. Induction is the reverse, is the gathering of particulars, and from there generalizing until you're looking for the commonality, looking for the bigger picture, and ultimately arriving at general principles. This is a little slide. This is what Bacon advocates you gather facts with a lot of observation, also experimentation. You gather them together into you generalize from them, perhaps conduct a few more experiments, generalize again from this first vintage, and ultimately come up with axioms. Axioms are not the beginning, not the start of the process as they are in Euclid. They are the end of the process. Those are effectively his laws of nature that are based on generalizing from many observations. Now, the reason why he insisted on induction over deduction is that he was critical, especially of Aristotelian philosophy that was supposedly deductive, that it never really engages with the world. It just starts with certain assumptions and it never escapes those assumptions, just deduces whatever you assume is what you get, and it never engages with the world, versus induction that does engage with the world and brings in more knowledge, more facts, more truths, and therefore can lead to new knowledge. Now, admittedly, induction is less certain than deduction. It's always dependent. The next experiment can demolish all the beautiful generalization that you built. So it's never as certain. But it is the way, according to Bacon, to engage and advance knowledge, and most importantly, induction for Bacon and for his followers in the Royal Society. It is the method of the experimentalist. And so when Wallis, at the beginning of the Arithmetica Inferentorum, wrote that he would proceed through induction, he was associating himself specifically with the experimental philosophy advocated by Sir Francis Bacon and later adopted by the founders of the Royal Society. He will study triangles, circles, squares using the same method as his friend Robert Boyle used to study the structure of the air, and his colleague Robert Hooke to study minute creatures under the microscope. In trying to establish a mathematical truth, he will begin by trying it out on several particular cases and carefully observe the results of these experiments. So he's going to try several cases, and at length, after he has done this repeatedly for different cases, he can reach a generalization. A general proposition will become known by induction. Okay. So Wallis's experimental mathematics is the basic tool of the Arithmetica Infinitorum and the foundation of his mathematical reputation. Wallis's goal in this work is to calculate the area of a circle, and to accomplish this, he tried to arrive at a number that would give the correct ratio between a circle and a square, with the side sort of the circumscribing square, a side equal to the diameter of with the side equal to the circle's diameter. Since the area of the square is 4r squares, and the area of the circle is pi r square, this comes down to calculating the value of 4 over pi, right, over here. And by the end of the work, Wallis managed to produce an infinite series that allowed him to approximate this as closely as he wished. And this was the series that he calculated. Now, Wallis began his calculation of the area of the circle much as he had begun the calculation of the area of the triangle by dividing it, looking at one quadrant of the circle, and he parsed it into parallel lines. Parsed it into parallel lines that together, one by one next to the other, that together comprise the area of the circle. Now, the longest of these is r, the radius. And the other gradually become shorter and shorter and shorter until they reach 0 over at this end. So if we mark the R, this is R0, this is R1, this is R2, this is R3, and so on. So they compose the area of the circle, while the circle is composed of the same number of items, but all of them are of the same length. R, that is capital R, capital R, capital R, all of these. Okay, that would be the circle. So, so together they are, the ratio is this, right? All those lines divided by the same number of the radius, right? That is the ratio of areas, or, since you can also write it in this form, because each of these lines is also defined by this, right? Is that pretty obvious, right? Each line here, each of the length of each of these lines is the radius minus the distance, the radius squared. The square root of the radius square divided by the distance from the center. All right, so this is the what he is looking for, and the way he goes about it, was he approached it through a series of approximations of similar series, drawing ever closer to the desired formula. And so this is what he does. Okay, so first of all, he says, okay, what is the ratio of, say, an arithmetic series divided by the same number of terms of the largest of the terms? So 0 plus 1 divided by 1 plus 1 is 1/2. Divided by 1 plus 2 divided by 2 is half. All of these are half. Okay, so you tried all these specific cases, and therefore, through induction, he concluded that this applies to an infinite series as well. Okay, limits, right? The limit when n approaches infinity of such a series is also half. Then he says, okay, what happens if it's not if to the sum of squares? So 0 plus 1 plus 0 here plus divided by 1 plus 1 is 1/2, and that is equal to 1/3 plus 1/6. Now, if you 0 plus 1 squared plus 2 squared is 5, divided by 3 times 4 is 5/12. That is 1/3 plus 1/12. And 0 plus 1 squared plus 2 squared plus 3 squared divided by 4 times 9 here. You keep approaching 1/3 over, closer and closer and closer as the powers, as the number of terms increase, and therefore he concludes that as n approaches infinity, 0 squared plus 1 squared plus 2 squared plus 3 squared, all the way to n squared divided by the same number of terms of the largest term is equal to 1/3. And so and then he does the same for cubes, and he concludes that the limit of 0 cube, 1 cube plus 2 cube, and so on, divided by an equal number of n cubes is 1/4. Okay, so he arrived at.
Excuse me. Was there some sense in which he really computed limits, or he sort of how did he treat that issue?
Right. No, he did not. He had a the notation is not his notation. This is of course modern notation. He had a table a table in which he explained, and he did in fact say that when it reaches infinity, you will reach those particular you will reach those particular results. Not with this notation. He had a table where he showed it, but he did say that you do reach that at infinity it actually reaches those numbers.
But the top slide is taken from his own papers, or is yours?
Sorry?
The top of the slide, I guess the limit notation he didn't have, but the top of the slide, this kind is from here. It's from
yes. The top of the slide. The top of the slide is exactly from him. Yes. The top of the slide is
the
exactly.
bottom is your rendition. Yeah. Thank you.
Yeah. The bottom line, I used modern notations just to show how he basically his method of induction from this so he used the method of induction to conclude from each case what the limit would be. And from those cases, he once again, by the method of induction, after trying for power 1, power 2, power 3, he concluded that this applies to all powers, and therefore, and this is his conclusion. For the power m, 0 to the power of m, 1 to the power of m plus 2, and so on, divided by this equal number of n to the power of m is equal to 1 over m plus 1.
Okay. Did he have a notation for powers? We do the exponents, or that's in modern?
He did use yes, he did use the power of notation. He did use that. Yes.
Thank you.
Yes, but not the limit. Not the limit notation. And he was one. Yeah, he was interested in notation. Like I said, he was the originator of the infinity notation. So this was his methodology. And just looking at and seeing why this was useful for him, because he was, for example, in the case of the cubes, he was basically calculating the ratio between this area outside a cubic parabola here versus the enclosing rectangle. That is basically what he was calculating. He was adding all those lines, and he was trying to do the same for a circle, which is a more challenging. But that is how he was approaching his. How he was approaching.
Quick question about Cavalieri. I mean, historians of mathematics attribute to Cavalieri that under x to the curve of x to the n, the area is x to the n plus 1 over m plus 1. Would he have known of that work?
I don't know. Yeah, I don't know exactly how Cavalieri demonstrated and how different it was from this. I can't say off the top of my head. But a lot of his some cases, Cavalieri does that too. He uses simple cases to demonstrate the effectiveness of his methodology, and Cavalieri does that too. In this case, he's using this to closely approach the area of a circle. Cavalieri was much more. In general, he was much more careful than Wallis. He really tried to, to avoid paradoxes, to go around. He had a lot of rules, very cumbersome rules, to make his system more consistent. Wallis didn't care very much, and anybody like Fermat, when Fermat asked him about it, he said, "Oh, just look at Cavalieri. He has if you want to, I don't worry about it. Cavalieri took care of all of that." It's not true, but it was very convenient for Wallis to just point to Cavalieri. He solved all those difficult issues. So Wallis viewed geometrical figures as material things, and therefore believed that just like any objects, they are composed of fundamental parts. Plane figures were made up of indivisible lines arranged next to each other, and solids of planes stacked on top of each other, just like Cavalieri. His preferred method for investigating mathematical objects was Baconian induction, which made his approach resemble that of an experimentalist in his laboratory more than a mathematician at his desk. Material, infinitesimal, and experimental, Wallis's approach was one of the most unorthodox ventures in the history of Western mathematics. Now, it would come as no surprise that not everyone was impressed with Wallis's accomplishment, and criticism were not slow in pouring in. Leading the charge was Fermat, Pierre de Fermat, whose critiques went straight to the unconventional heart of Wallis's approach. He condemned Wallis's casual use of infinitesimals, which uncritically assumed that one can sum up the lines in a plane figure to calculate its area, but he reserved his harshest criticism for the Englishman's method of proof. One must be extremely careful using the method of induction, Fermat warned, because it allows one to propose a rule that, to quote, will be good for several particulars, and nevertheless will be false in effect and not universal. The method can be useful in some circumstances, he conceded, but must not be used as for the foundation of a science that from which it is deduced, as does Mr. Wallis. For that, one must settle for nothing less than a demonstration. The unavoidable implication that Wallis's inductions were not demonstration was left unsaid. But Wallis was unmoved. He artfully deflected Fermat's valid criticism of infinitesimals by claiming, quite wrongly, that all issues had already been addressed by Cavalieri. If Fermat nevertheless wished to construct all the proofs in the classical form, Wallis wrote, it was free for him to do so, but he might spare himself the labor because it was already done to his hand by Cavallerius, that is Cavalieri. Wallis was equally unimpressed by Fermat's critique of his method of induction. Proof by induction, here's Fermat. Proofs by induction, Wallis claimed, are plain, obvious, and easy, and require no additional demonstration. If any think them less valuable, he wrote, because not set forth in the pompous ostentation of lines and figures, that is in the Euclidean form, I am quite of another mind. Pedants like Fermat, he continued, are a distinct minority. Most mathematicians that I have seen, after such induction, continued for some steps and are satisfied from such evidence to conclude universally, and so in like manner for the consequent powers. And such induction has hitherto been thought a conclusive argument. Wallis's inductive proofs are not meant to be infallible legal deductions, but rather strong persuasive arguments aimed at swaying his audience. It was in the end not irreproachable logic, but the consensus of most mathematicians which stamped his results as conclusive arguments. So if Wallis's approach was unacceptable to orthodox mathematicians such as Fermat, for his colleagues at the Royal Society, it was a solution for a vexing problem. As I mentioned earlier, they had a problem with mathematics. They were advocates of an experimental approach and worried that mathematics was overly dogmatic, overly definite, and the cornerstone of a vision of knowledge and the state that the society grandees viewed with horror, Hobbes's totalitarian commonwealth. As they saw it, whereas experimentalism stood for moderation, toleration, and peace, mathematics was the tool of advocates of dogmatism, intolerance, and their inevitable outcome, civil war. And Wallis is offering them a solution to that conflict because they do not want to leave mathematics out in the cold. They know that mathematics is essential to the scientific project. So Wallis proposed a unique brand of mathematics that is as powerful as the traditional approach, but also perfectly in line with the society's cherished experimentalism. A flexible mathematical approach which was accommodating of dissenting views and modest in its truth claims, precisely the kind of mathematics that the Royal Society could endorse. In almost every respect, Wallis's mathematics replicated the experimental practices of his associates at the Royal Society. It investigated external objects, not constructed ones. It relied on induction, not deduction. It never claimed to have arrived at an absolute truth. Most importantly, the final arbiter of the worth of a demonstration was a consensus of men, not logical compulsion. It was precisely the kind of mathematics that one would expect from the leading mathematician among the founders of the Royal Society, a modest, tolerant, and consensus-driven mathematics designed to encourage the same qualities in the body politic as a whole. Thanks to Wallis, mathematics could now join with experimental practices to promote true science, proper social norms, and a peaceful social and political order. All right. Thank you.
Bravo.
Thank you very much for fascinating talk.
Thank you.
But I'm a little disappointed. John Wallis scooped me. That's exactly my philosophy with very, very minority view today. But so it's really my soulmate. So thank you very much. Other questions to Amir about the talk?
Well, first of all, it was beautiful and absolutely appropriate for Doran's seminar. I mean, it's a perfect fit, right? What you've missed out, I think, are questions of priority. And these were quite important at the time. For instance, people, when they discovered something, maybe inductively by inference, they would write little anagrams, little secret messages to prove that they knew something.
Yeah.
And that goes rather against this consensual attitude that you have. I mean, we know that there are very serious priority disputes in the Royal Society between Hooke and Newton. So, I mean, would you like to comment on that? I mean, how important there must have been undercurrents of priority in all of this.
Yeah. First of all, Newton was certainly an exception. I mean, he was, of course, the brightest star of the Royal Society, but he did have quite a bit of trouble with the Royal Society in the early years, in the years that I am talking about here, because Newton annoyed the grandees of the Royal Society, but by being too definite, by insisting that his approach was just right. That was he did that, of course, with his mathematics. He did it even in his experimental practice. It was the wrong kind of experimental practice. It wasn't the kind of open-ended, like Boyle, oh, this is what we know right now, but who knows what, never wanting to say anything definite. No, Newton said, I have conducted, like, with an experimentum crucis, a critical experiment, as he did, for example, with his optics, and he said, well, you follow me. That resolves the issue. Yeah, I'm being a good experimenter here, but I'm not going to pretend like this is not true. This is true. I resolve the problem. And he did the same with his mathematics. And when he was criticized, he kept working towards making it more and more, as we would say, kind of rigorous and consistent. So part of his problem with with Hooke was certainly personal, and but it was also a matter of it was also methodological. Newton, needless to say, insisted on his priority and on his and on his credit, uh, um, and yeah, and he rubbed people the wrong way with his approach. Later on, he became kind of the patron saint, superstar of the Royal Society, and then they all gathered to his banner to prove his priority. But his approach was rather at odds with the main thrust of the early generations and generations of the Royal Society, where even later generation, when they said, okay, Newton is Newton. Newton discovered the truth, but now that is done. God said, "Let Newton be," and all was light. So he discovered the secret of the universe. And now we'll go back to the experiment. Want to know more? We'll go back to the experimental method. There is a very strong experimental streak that continues even beyond Newton.
Thank you.
So Newton was not well liked when he was young?
Well liked? I don't think he was ever well liked. He was admired, but I don't think he was ever well liked. No, not anywhere. And he certainly, he was arrogant, and he knew that he was Newton and you were not, and he let you know it, I guess. Yeah. So yeah, he did not. And he also his approach was not, Boyle was also always so very courtly and polite, and at least modest in his claim and in his appearance. And Newton was not at all. He was right, you were wrong, and that was the end of it. Yeah.
I'd like to make a comment. You began with an experimental proof about the area of a triangle, but many years later, people had the idea of taking a triangle, cutting it up into a finite number of pieces, and reassembling the pieces to form a rectangle. And so there's this beautiful theorem, usually known as the Bolyai-Gerwin-Wallis theorem, which states that if you have two plane polygons of the same area, you can cut one up into a finite number of pieces and reassemble them to the other. And so for a triangle, any triangle, you can do that to a particular rectangle, and that's another experimental approach to getting the area of the triangle.
Oh no, that's really that is really interesting. That could also that's sort of also another kind of hands-on sort of with kind of based on material intuition of taking.
And then many years later, Max Dane showed that you couldn't do that in 3 dimensions, that you couldn't cut up a cube and a regular tetrahedron into a finite number of pieces and reassemble the pieces of the tetrahedron to get a cube, even though they had the same volume. So there's a lot of very beautiful, both theoretical and experimental mathematics in that domain.
Oh, thank you. That is really interesting. Yeah.
Sorry. Yeah. My co-organizer cannot have a microphone, but in the chat, he has a few questions for you, Amir. Can you look at the chat?
And the what?
As a chat.
The chat. Okay, let me look at the chat just a second.
Stoyan Dimitrov has a few questions.
Okay, let me stop the share here. All right. Yeah. Right.
Can you see it?
Continental Europe, Europe at the time. Well, of course, there's Cavalieri and Torricelli. I think Roberval, I believe, sympathetic, and there were even there was Stefano Angeli in Padua, and there were even, I mean, there were in Italy, and we know that from manuscript writing, there were mathematicians who published who could not really publish in Italy at the time because of the repression of this approach of the infinitesimalist approach in Italy, but that were in their private correspondence actually developing similar ideas. They were the true heirs of Cavalieri and Torricelli, but they did not have they did not have the platform that Cavalieri and Torricelli did. The exception was Angeli, at least for a while, until he too was warned off that path. Yeah, but really, the center of infinitesimal mathematics was really had moved out of Italy by this time. I mentioned Roberval in France and Wallis in England.
Could I put in a word for Marin Mersenne, please? Because I think he has some correspondence with what you've been saying about consensus. He was very much concerned scientific and mathematical communications. Indeed, we only know of Roberval's work because Mersenne communicated it. He'd been educated by the Jesuits, but he didn't want to be a party to this philosophical suppression of the infinitesimals. He wanted people to exchange their scientific knowledge, and whilst we don't owe any important mathematics to Mersenne, I think he was occupying some of the roles on the continent, albeit in the 1640s, that you're talking about later at the Royal Society.
Yeah, that's true. He was not a Jesuit. He was a member of a small order, the Minims, and most small orders did not like the Jesuits precisely because the Jesuit had.
But he was educated as a Jesuit.
He was educated. They had the best educational system, and he was educated as a Jesuit. Yeah. But then as a minim, he was very suspicious of the dominance and the totalizing view of the Jesuits, and he did exactly that. He was like this. He had connections with everybody, and brought them together.
Any more questions for Amir?
I'm seeing Wallis was known to be anti-Catholic. Was the only reason for this opposition he faced from the Jesuits on was his experimental way of doing math. The Jesuits certainly opposed what he was doing, but they were not really concerned with Wallis as they had been with Torricelli and Angeli and Cavalieri in their day. They had no presence. In England, and so he was, there was no way that they could actually influence the intellectual landscape there. He was a Presbyterian divine, and he was certainly anti-Catholic, as were pretty much the vast majority of his fellows at the Royal Society. But impressively, the Royal Society itself did have Catholic corresponding members on the continent.
Yeah, I think that's actually very important, that the Royal Society didn't want to get itself divided on religious issues. And you've got to remember, we've had a civil war Charles in the Restoration, but James II had Catholic sympathies, and it wasn't clear which way England was going to go. I mean, the Glorious Revolution of 1688 settled that question, but it settled it on essentially consensual grounds, with the merchants and the Mayor of London and the Royal Society deciding we want an end to religious wars. People had to be quite careful how they expressed their religious and political sympathies in the 1660s, 1670s, and the Royal Society was a haven of intellectual discussion that avoided such dangerous questions.
Right. I'm not aware. That was exactly their point, to avoid those kind of divisions, and that was the whole point between the Anglicans and the Presbyterians and Independent and so on. I may be wrong. I'm not aware of actual English Catholic members of the Royal Society, but I may be wrong. I am not. That's an interesting question, whether they would extend that tolerance to English Catholics. I'm not sure. Yeah. I felt like Descartes described himself as an experimentalist in the discourse on the method. Yeah, so Descartes starts out by seeking certainty. He is very dissatisfied with the state of knowledge, and he believes that the way to arrive at certainty is through absolute, clear, and distinct reasoning. That is, first of all, getting rid of any kind of doubts or any kind of confusion in our mind, erasing all of that, starting from the only thing that we know for sure, I think, therefore I am. And from there he goes to God. There he proves the existence of God, and then God cannot be a deceiver, and therefore strict rational reasoning has to be correct. Because if it's not, that means that God is a deceiver, and that goes against what God is and the definition of God. So, and from there he builds step by step what the world is like through rigorous reasoning. Now, ultimately, and I think that is what you're referring to with experiments. Ultimately, he arrives at a point where he realizes that you can be a very good Cartesian, follow all the strict rational principles of what the world is like. Everything, matter is space, space is matter, everything is matter in motion. All of that, be a very good strict Cartesian. But nevertheless, there's always more than one explanation for any phenomena, right? Why do things? Why do objects fall, and so on? Why? Any natural phenomena, even if you do follow those very rigid and necessarily true principles, there are still more than one possible explanation, and that is where experiment comes in for Descartes. At that point, that is as a point when you have to decide between competing good. They're good explanations. There's more than one, several explanations. All of them adhere to proper Cartesian principles, but you need experiments in order to decide: is it this? Is it this? Is it this? Is it this? So he did use experiments, and that is sort of a concession for the fact that even his very strict rational reasoning does not ultimately lead to the certainty that he was seeking. You ultimately, at that point, still need experiment. So he has some small role for experimentation, perhaps smaller, anyway, important to be sure, but the basis of his reasoning is pure logical deduction, and then in the end he has a place for experimentation. And you can say something somewhat similar about Bacon. Bacon went the reverse. He was very skeptical of pure reasoning. He thought that's just fantasies. That you have to really rely on induction, on a many observation, and try and arrive at conclusions for that. But he still had a small place for mathematics. Things come by things come by number and measure and so on. So he didn't entirely exclude mathematics, but he confined his role, and that was sort of the mirror image of what Descartes was doing with experimentation.
Anyway, thanks so much. I think it's a good time to stop. Well, thanks for a great talk, and the recording will be available in a few days. We'll let you know. And meanwhile, you're welcome to email me the slides for posting. Thanks everybody for coming, and see you next week. Bye-bye. Thank you.
Yeah, thank you everybody. Okay. All right.